Good morning. Myself, Dr. K. Viswanath Allamraju, Professor at Institute of Aeronautical Engineering, Dundigal, Hyderabad. In the last class, we covered one of the problem on cantilever beam. The cantilever beam is subjected to UDL and point load. Now, we are going to study some more problems, how to solve by using, how to find out shear force and bending moment calculations by using sign conventions of shear force and bending moments. Unless until we have understand how to apply the sign conventions, the values the observed values becomes wrong. Next, we are going to study the problem of the combination of 2-point loads and UDL, uniformly distribution load. Let us see the problem. In this problem, what is there? The UDL is acting on this. This is the UDL portion. This is the UDL portion. What is the portion of the UDL? It is at a span of 2 meters from point D to point C. There is 1 kilonewton per meter. But there is a 2 point loads are acting. One point load at extreme, that free end at point B, and another point load is in the middle of A and D. Not in the middle of at point E. It is acting at 3 kilonewtons at near to the fixed end at a distance of 1 meters from fixed end. Now, how to solve this? But the total span of this beam is 5 meters. The total span of the beam is 5 meters. So at a span of from fixed end, at a span of 1 meters, there is 3 kilonewtons. And at a span of 2.5 meters, the UDL begins up to 2 meters. Next, from at a distance of point C to point B, there is 0.5 meters point load is acting. That is, value is 2.5 kilonewtons. So how to solve? So here you have to draw shear force. First, shear force, how to draw it? So let us begin how to calculate the shear force values at points A, point B, point C, point D, and point E. As we have mentioned, as we have studied in before video, that we have to start if from free end. Calculation begins from free end. So shear force values are to be calculated from free end, that is the point B. At point B, consider carefully, at point B, the load is downwards. Suppose if you are coming from this direction, point B, the point B means section is after the point. After the point section is then what is the right side of the direction? Right side, the point load is acting downwards. If the force is downwards, it comes under positive. Now that's why 2.5 kilonewtons acting downwards on the right side of the section line. These are the section lines. Why should we go for section lines? These section lines helps not to make mistakes in calculating shear force values. Let us see here. There's a point B acting downwards. So 2.5 kilonewtons is positive. So at point B, it's positive. Now up to this positive, up to the section line extend to point C, the same force is acting. So what is the force? The section line. Now here, now the section line passing through. Now the section line moved to up to point C. Though this is the section line, right side force is downward direction, then from sign conventions, we can understand is the positive shear force. So up to point B to point C, the shear force value is 2.5 kilonewtons. It's a constant line. Next go for point D. What is the shear force at point D? Shear force at point B is 2.5 kilonewtons. Point C is 2.5 kilonewtons. What is the shear force at point D? Now shear force at point D, there are up to here. Now section line goes up to here. Shear force. Now section line is up to point D. This is a section line. Now you consider this zone. That is our values. We have to consider it. Right side direction, because we are moving from right to left. So right side portion, what are the loads are acting here? There is 1 into UDL is acting. 1 into what is the span of the UDL? 1 into 2. 1 kilonewton per meter into 2. that is 2 kilonewtons acting downward direction plus 2.5 kilonewtons also acting downwards. So right side section line, downward direction, right side section line, downward, right side section line, downward direction is positive. So 2 plus 2.5, that is 4.5 kilonewtons. At D, it is 4.5 kilonewtons. Next, what is the next point? Point E. Consider point E. Now section line is moving. Where is the section line is moving? Now section line zone is up to here. This is the zone we have to consider. At point E, downwards 3 kilonewtons. And point D, this UDL is acting how much? The total UDL is acting 2 kilonewtons. This is 3 kilonewtons, this is 2 kilonewtons and 2.5 kilonewtons. Section line right side all are downwards, so positive. 3 plus 2 plus 2.5. What are the values? 5 plus, that is 7.5. At E, that is 7.5 kilonewtons. Now, after this calculating, next at point A, the same load is passing through from point E to point A, that is 7.5 kilonewtons. By considering these values, we have to draw shear force diagram. So now, whenever UDL is acting in shear forces, in calculating shear force, the variation of shear force is linear at UDL, whereas at point loads it's constant lines. So these are the lines observed. These are the points as B. At point B, 2.5. Again, we have to write here so that understand better. 2.5 at point C. Point C, 2.5 kilonewtons. At point D, 4.5 kilonewtons. Point E, 4.5 plus 3, 7.5. At point A, 7.5 kilonewtons. Okay. Now, what is the total load here? That is B, C, D, E, A. Let us begin at B, 2.5 kilonewtons. 2.5 kilonewtons. Next, up to C, it is a constant. Next, point E to G, point C to D, it is increasing, varying. That is 4.5 kilonewtons. It is a straight line, inclined line. Next, 4.5 up to point E, it is 4.5. At up to point E, it is 4.5. At point G, exactly what is happening? Increasing to 7.5. At 7.5 to up to point E to point A, it is again constant. Now you join this wall. This is a baseline. Generally, you will observe this is the baseline. From that, it will come increasing and again increasing here. Then it will come out. Then what to do? We have to close the thing. We have to close it. Then this is the shade. How the variation of shear force is changing at various points. Here, in this case, it is at point A, point B, point C, and point D. Now we can understand here why we have to study this shear force calculations, because we can understand in real field structures there will be different types of loads will be there. It is in the form of various structures such as sofa sets, almirahs, it is called cupboard, it is biruas, etc. So what we have to use it. So because of those those loads acts on the whole structures. So how it causes effect? It causes in the form of shear force and bending moments. Now that's why we are calculating here. Now here it is up to point B to point B at 2.5, point B to point C it is constant, but point C to point D it is varying how much? 2 kilonewtons are varying. It is increasing from point C to point D is 2 kilonewtons increasing. That's the 2 plus 2.4, 4.5. Whereas from 4.5 after point E, it increased again to 7.5. It is constant up to 4.5. Up to point E, point D to point E, it is constant 4.5. But from 4.5 at point E crossing, if you're just crossing point E, then what happens? It increases the effect of point E. At point E, it is again 3 kilonewtons acting. So it increases the shear force that went to 7.5 kilonewtons. It is constantly maintained up to point E. So at point A, what is the load? Shear force is acting 7.5 kilonewtons acting at point A, shear force. So that's why if you hold here at fixed end is maximum shear force acting. Whereas at free end, what is the shear force is? Minimum, very least, low value, that's 2.5 kilonewtons. If you hold anything, if you hold the cricket bat at the free handle like that, the maximum load effects on the fist. So because this is the span of the total cricket bat, the whole complete weight passing acts at the fixed end. So here, by observing this cantilever beam, you can understand it. The maximum shear force is acting at point A, and minimum, very low value of shear force is acting at point B. Next, how to calculate second part, that is bending moment calculations. So how to calculate bending moment values at various points, point A, point B, point C and point D. So we have to draw first of all bending moment sign conventions. So in the case of shear force, in the case of cantilever beam, all loads are acting downwards. That means the bending moment is downward direction. That is, it comes out of this case, that is negative bending moment in cantilever beam. So negative values will come. What is at point B? Bending moment at a point B is 0. And what is bending moment at point C? Is the force 2.5. What is the distance? Moment distance. That is point at this point. Okay, about this point C, we are taking moment value. So this 2.5 kilonewtons into 0.5 negative minus 2.5 into 0.5. That is 1 point negative value of negative 1.25 kilonewton meter. Up to point D, coming to the point D. This point D, at point D, what are the loads are acting? About that point, this point load is acting and UDL is also acting. So what is that UDL? That UDL is convert uniformly distributed load. You are going to convert into point load. So how it is uniformly distribution? 1 kilonewton per meter. What is it? Into 2 meters. That is 1 into 2. 2 kilonewtons are acting. But where it is acting 2 kilonewtons? From where? What is the distance? It's the middle of this UDL. What is the middle half of the UDL distance? 2 by 2. That is 1 meter. So here it is 2 kilonewtons point load. That is 2 kilon UDL converted into total load. That is 2 kilonewtons. The distance from that point is half of the total UDL distance. That is 2 by 2. That is 1 meter. That is 2 into 1 meter. Negative value of minus 2 into 1 meter minus 2.5 into what is the distance? Point B2 about this point D. 2.5. Total value it comes under as minus negative 8.25 kilonewton meter. So far we calculated at point B, point C, point D. What is the next point? Next point is E. At this point, again UDL is acting and point loads are acting, but the distance is increasing. So the distance is UDL 2 kilonewtons, negative 2 kilonewtons. This is a 2 kilonewtons downwards. 2 into what is the distance from this point of action to point E? That is 1.5 plus 1, 2.5. 2 into 1.5 minus 2.5. What is the distance? Point B2 up to point E. 1.5 plus 2 plus 0.5. The total distance is 2.5 plus 1.5, that is 4. So total distance 4. So 2.5 into 4 minus 2.5 into 4 minus 2 into 2.5 meters. Then you can understand this is the 15 kilonewton meter. Now again consider bending moment at point E. What is the bending moment at point E? The bending moment at point E is minus 2.5 from point B to you come. What is the distance about point A? That is 1 plus 1.5 plus 2 plus 1.5 distance minus 2.5 into this total distance, that is 2.5 plus 2.5, that is 5 meters distance, minus UDL load, that is UDL total load is 2 kilonewtons. From here to this distance 1 plus 1.5, 2.5 plus 1 meter, this is 1 meter, 2.5 plus 1, 3.5 meters, minus 2 into 3.5 meters minus 3 into 1 meter. This is what, again you can see it, this step here, minus 2.5 into 5 minus, that is make it, they made it 5, minus 2 into 1, yeah, minus 2 into 1 into 1 plus, yeah, the total distance minus 3 into 1. Okay, that is the total distance, is the total value, moment value is minus 22.5 kilonewton meter. How to draw this? You can understand by drawing the bending moment diagram. You can understand how the variations of moment values can be observed at various points. In this case, it is point A, point B, point C, and point D. So at point B, it is 0. At point C, what is the point C value? That is minus 1.25 kilonewton meter. At point D, minus 8.25 kilonewton meter. At point E, that is 15 kilonewtons. At point A, that is 22.5 negative value. So wherever the UDL is there, in the case of bending moment, that UDL gives the parabolic curve. So point C to point D is a parabolic curve, and point B to C is a straight line. Again, point D to E is a straight line, is all straight lines. So here the maximum bending moment takes place in spite of the direction. The value is maximum here 22.5 kilonewton meter at fixed end. It is 0 at the free end. Whereas if we compare shear force values versus bending moment values in this problem, at shear force is maximum at fixed end. Similarly, bending moment is maximum at the fixed end. Bending moment is 0 at the free end, whereas shear force is not 0, it is 2.5 kilonewtons at free end. So you can understand from this that at fixed points maximum values occur, shear force and bending moment values are observed at fixed ends, whereas at free ends minimum values are very low values or least values are observed at free ends. So wherever we are constructing this cantilever beams, the fixed end should be strong enough. Otherwise, the failure of the structure can be taken place.
Like, share and subscribe. Hit the bell icon for more updates.